Hello everyone, welcome to my presentation. This presentation is designed for IGLC conference paper, and the title is Applying Heat Maps to Define Workspace in Construction based on real-time tracking system with coordinated positioning information. My name is Zhao. I'm a Master of Science from Royal Institute of Technology, and my major was real estate and construction management. Now I'm currently in my fourth year of my PhD studies at Aalto University, Finland. My research topic is using real-time tracking system to improve production control in construction. And my PhD supervisors are Professor Seppänen and Professor Peltokorpi. And for the introduction of the paper, so construction sites are often in a very messy environment, which leads to massive efficiency loss and waste due to management reasons and resource mishandling. So over the past years, previous studies have confirmed that there is substantial room for productivity improvement in construction industry in terms of the scheduling, labor training, and quality control. Therefore, there is a need for automatic generated information for on-site resource management, such as labors, materials, and equipment. And Workspace is a key resource in construction sites that are required by construction activities. Alongside workspace management in construction, several lean methods such as location-based management system and takt time planning are also applied to eliminate waste and improve productivity at work location on site. And in previous studies, research have also tried to apply real-time tracking solutions and heat map applications in construction. For example, research have tried to implement three-dimensional modeling to detect and track moving or static object boundaries in real time based on video cameras. And later on, heat maps generation has also been proposed, where the researchers applied heat map generation in construction to map at-risk behaviors of workers. Yet, the application has been served only for safety planning instead of operations management purposes. And also research have also implemented a Bluetooth low energy tracking system according to trilateration method to acquire the real-time location of resources and movement in job sites. And in their results, the formation from multiple single points of detected coordinates has a very high deviation from the original path. And they only carried out data analysis on a single person simulation. So they only focused on technical requirement and the description of system architecture, but not on the use cases from the lean perspective in construction. So based on all of those, we have proposed the two of the research questions. So first is, how can a coordinate-based real-time tracking system be applied to real-size construction projects? And second is, how can heat maps of the worker's presence on site be used to serve lean approaches in construction, such as takt time planning and uninterrupted presence detection? So we believe through this research, the construction industry can benefit from automated workspace detection based on heat map generation from real-time tracking system, which would also complement other lean approaches in construction with goals to improve management efficiency and eliminate the waste. And for the case selections, a single case study approach was selected as a research method. The location of the case was in a Chinese city close to the capital, Beijing. The construction project was undergoing a large amount of MEP work at the time of testing a large shopping mall building. For our system site implementation, the real-time tracking system was implemented on the second floor at the north corner of the building, where the MEP workers were scheduled to do the pipeline assembling task at the location that time. The second floor is a big indoor open workspace with a regular grid of load-bearing pillars, and the tasks should proceed following the regular direction of continuous work. Therefore, the layout of the test place and the task nature of the work is suitable for indoor positioning with this feature of coordinate detection and the generation of heat maps. So here I'm gonna briefly describe the infrastructure of the tracking system, and it was part of a collaboration with School of Electrical Engineering at our university. The system, which is capable of tracking individuals, materials, and tools with coordinates, comprises of the following separated parts. First is Bluetooth low energy beacons, which transmit data using Bluetooth low energy radio technology, and also can be detected by any Bluetooth devices. And second is the gateways, which are intermediate entities that collect data from beacons, aggregate and finally send them to the cloud. And the data are transmitted in approximately 1 second, in 1 second time interval. And the third one is a cloud, which is the brain of the tracking system and comprises of the different modules. The cloud receives all the data using MQTT, message queuing, telemetry transport. And for the on-site gateway placement and validation routine, we managed to install 7 gateways on site and attach them to the building pillars, approximately 1.5 meters above the floor. And each pillar is about 9 meters from each other. Therefore, an ideal coordinate integrated floor plan can be modeled. And the red dots in the figure on the right were the validation routine, where a researcher simulated a worker's possible on-site path and compared the coordinates of each test point along the path with the system captured records. And we pinpoint each pillar with coordinates and set the point of T2, which is very down and to the left in the figure as our original point. So then we could do the validation. So the validation results based on 3 different measurement intervals on each test point along the path. Those are 30 seconds, 1 minute, and 2 minutes. The measurement intervals refer to the time the researcher purposely has stayed at each test point before moving to the next one. So the results in the table suggest that with bigger measurement intervals, the average deviation and the standard deviation of all recorded points are lower. The reason is that if a person stays at a test point longer, like 2 minutes, the more stability there is for the tracking system to detect the location of the person. However, the lowest average deviation between actual test points and system captured coordinates is still more than 10 meters away, and this is more than 1 pillar away in real situation. So therefore, for single dot of coordinates by the tracking system is not that accurate. However, it is also still possible to reduce the movement from the heat map generation. So for the heat map generation, multiple points are generated per second to pinpoint the coordinate of the actual points in the system. So there were more generated points as they are closer to the actual point, so which makes a higher density of the points in the figure on the right, for example. So therefore, a deeper colored area, which indicates a higher density, is of a greater probability to reflect the real place of a worker at any given time. So, so we followed this, this method to generate the heat maps for the workers. And first we generated the heat maps with hourly intervals. So the heat map with hourly intervals can easily identify which hour of the day could be the workers most likely to work time based on their movement density on site. And the worker was detected for intensive on-site presence, for example, between 9 a.m. to 11 a.m. at the east corner of the test site, and between 2 p.m. to 4 p.m. at the middle and east corner of the test site, while he was not detected and probably also was outside of site between 12 p.m. to 1 p.m. So the heat maps can be used to first fast check workers' workspace in different time intervals and also during the different time hours. And then we try to generate the heat maps in more detail. The figure on the right demonstrates the captured workspace where one MEP worker has conducted his task between 2 p.m. to 4 p.m. Based on the high level of uninterrupted presence detected during this time. So it is reasonable to think that with a deeper color of the heat map, the worker is more likely to do the value-adding activities because of a higher frequency of the position points, which is detected within the deeper color area. So heat maps connect the dimensional and temporal data and integrate them into real-time tracking system. So site managers are able to monitor site happenings through an automated process. So then we propose the 3 use cases of this heat map application. So first is analyze and tagged areas. So for projects that implement tagged time planning, heat maps can automatically detect the workspace over time and comparison with assigned tagged areas to see if they match in real practice. Furthermore, heat maps can also be generated to visualize how buffer capacities between tasks is followed and provide in-time feedbacks for managers to adjust resources to ensure a good construction flow. And second is to identify threshold values for workers' presence in workspace. Our previous research has proposed the concept of a threshold value for uninterrupted presence on site, where we argued that a worker needs to stay at workplace for a certain period of time so that it can be counted as an uninterrupted time, which is correlated with value-adding time. So because heat maps are generated on a basis of the density, so the actual threshold minute can be calculated according to the heat map of that worker in question, where his or her workspace is detected. So therefore, the density of the presence of the worker in question should be an indicator of actual threshold value of his or her uninterrupted presence. And the third one is forecasting potential workspace congestion. So heat maps generated by real-time tracking system can be used for that. because it can predict the interference degree among different tasks during the same period of task conducting time, because the system supports multi-resource tracking. For instance, if a certain area is detected with a very high density of presence at the same time from other several task crews, the heat maps could also raise alarms in advance for site managers to notice the potential work congestions in that area. For the implication of this research, our findings indicate that it can provide both dimensional and temporal data through an automated and illustrative process in the construction environment. And on-site temporal data, such as time spent of workers, connects with the value-adding activities. And also on-site dimensional data, such as workspace area, connects with the resource management, such as labor, equipment, and material. Therefore, heat maps that includes spatial temporal data can generate a more straightforward space-loaded production model where value-adding activities can be potentially detected. And for a single detected point with coordinates has a very high system inaccuracy and variation, but heat maps can still build fuzzy outline to estimate workspace based on the density of on-site uninterrupted presence. And some limitation and the outlook for the future. First, the limitation of the method in this paper comes from the system inaccuracy for the detection of coordinates. So the applied tracking system generates one researcher's coordinates during the validation process for an average deviation of more than 10 meters. Therefore, a single point is lacking evidence to be very accurately detected on site. So this could hinder the generation of heat maps, especially for identifying the border of estimate workspace. However, this paper demonstrates a prototype proof of concept implementation, and it is possible to implement a commercial solution with much better accuracy. So we think the result based on this accuracy can provide a pilot dataset to analyze the proposed use cases in the paper for link purposes. And second, only based on this tracking system, what has actually happened on site still remains unknown. So therefore, a more advanced positioning system featured with more accurate coordinate detection should be applied in future research, such as vision-based technologies. For conclusion, the paper has illustrated a case study where a BLE, Bluetooth Low Energy Based real-time tracking system, is implemented to capture workers' coordinate data in a construction site. The research is followed by on-site system implementation, coordinate detection, validation process, heat map generation, and use proposals of heat maps. Though we found that single point of coordinate in this tracking method has an inaccuracy, the heat maps generation based on the density can still outline an estimate of worker spaces with fossil borders. Based on this, we propose the use cases such as tagged area detections, estimate threshold value, and forecast potential workspace congestions. So the heat maps approach applied in construction provides an innovative alternative to estimate workspace on site with spatial temporary data obtained by real-time tracking system. That is all for my presentation. Thank you very much.